Can I be heard all right?
Yeah.
Okay, so
Okay, so we are continuing with the fourth part of Gero's lecture on crystallization in classical particle systems. Thanks, Gero.
so thanks, yeah, great school, and thanks also on this occasion for arranging the great conference dinner yesterday. So so that was very enjoyable. So yeah, here we go. So I started with a general overview of crystallization problems. So okay, so some of this seems to be not working. Okay, so no, this way it works. So crystallization is about the fact that at low temperature atoms and molecules self-assemble into crystalline order and special shapes. So I explained some examples. I showed you some examples on the first day. Then we looked at the mathematical models, so especially molecular dynamics, statistical mechanics, and energy minimization. And all three, they're connected by a long time and low temperature limit. And so prototypical energies for atoms of the same type would be Lennard-Jones type potentials. So they're repulsive at short range, attractive at long range, and have a sort of potential well kind of here. So then I started talking about which in 2 dimensions is the best known crystallization theorem. It's the Heitman-Radin crystallization theorem, that when you take a brittle limit of the P2P Lennard-Jones, so you make the potential very thin, depth 1 sitting at radius 1, so you get this potential here plus infinity for radius less than 1, so it's sort of hard disk thing, but you get a penalty -1. So in that sense, it's different from the hard disk system because it's sticky disk, so you get a reward -1 for binding. So that is modeled in here, and then 0 at long range. And so then there's the wonderful theorem says that for any number of particles, minimizing configurations are up to 1 overall translation and rotation subsets of the triangular lattice. So it's a global rigidity. You only have 1 orientation across the whole ground state. So that's the amazing thing. And I think that's the only case where something like this has been proved. And so we have this new proof based on discrete differential geometry. So the old one, it was clever, but used some numerical value of the minimal energy and did some iteration with that. And so we think our proof is much simpler. So here's the geometric energy decomposition again. So for a soft potential, you have 6 terms. For the Heitman-Radin, the last 2 are gone, so you only have 4 of them. So no elastic energy for Heitman-Radin. Either you're bonded or you don't interact at all, and also no non-bonded interaction. So because it's short range, and so then it's -3 times number of particles, plus perimeter, plus defect measure, plus Euler characteristic, and so the different terms I explained that what we like about this decomposition is that they indicate the different mechanisms of energy lowering. So for example, the P of X, so the perimeter, it penalizes long change. Yeah. So instead of a long change chain has a huge amount of perimeter, so that's not favorable. You should condense it into a bulk region. But it's really this term and only this term. So the long chain has no defects. It's just a straight line of bonds. Now the defect measure, it wants the faces to be triangular. So it doesn't like vacancies in the middle, you know, like no holes in the middle. So once that, the Euler characteristic is also interesting. So you think of it as a topological invariant, but the bond graph of a particle system can change its topology by aggregating clusters. And so the Euler characteristic counts the number of connected components. So it aggregates 2 separate clusters into 1 cluster. So that gains your Euler characteristic. It doesn't change the perimeter, doesn't change the defect measure. And then these 2 terms are elastic. So elastic energy, I want to discuss this. So it rigidifies stretched or compressed bonds to unit length. So wants the bonds to have unit length. And so the non-bonded interactions, so they're tricky ones for long-range potentials. So in that sense, my so the models studied here are somehow dual to the models Ed Saf was talking about the tail-heavy wreaths. Yeah. So it's really a different regime. Okay. So yeah. So here we go. So now what I didn't explain is how one proves this Heitmann-Radon theorem. So I want to start by explaining the proof. So it's just 4 slides. So it's not very long. And it's different from the linear programming bounds type approach. So it's more an induction on the size of the clusters, but the induction has to be done in the right way. So if you do the induction in a stupid way, like adding 1 particle, it's not good because it gives a huge rearrangement. So we'll see how this goes. So let's recall the energy decomposition for Heitmann-Radon. The elastic energy and the non-bonded energy are gone. So we have a universal constant for the n-particle systems, then the perimeter, defect measure, and Euler characteristic. So perimeter equals number of boundary edges with the right way of counting them. Defect measure is number of quadrilaterals plus twice number of pentagons, 3 times number of hexagons, etc. So penalizes the non-triangular faces, and the less triangular they are, the bigger the penalty. And the Euler characteristic is just the connected components. So we're interested in minimizers. So the first thing we can do is assume that the Euler characteristic is 1. So because what do you do when it's not 1? You take 2 connected components, you move them towards each other until the distance between the 2 connected components is exactly 1, then you have gained 1 bond. Okay, so with this argument, I mean, we're talking about finite systems, so it has finitely many connected components, so you can do this move until the thing is connected. So minimizers are connected, so the Euler characteristic is also gone, and so then it's cool, so you only have 2 guys to play with, so it's the perimeter versus defect measure. And they're somehow in competition. I will explain how. And so the second thing, so that's a simple thing. So if there's no defect, so all faces are triangles, and the boundary of the configuration is a simply closed curve, then the configuration is a subset of the triangular lattice. So that's a simple fact. Because in this case, so a triangle means all equilateral, all distances are 1. And so the only way you can form a connected set out of equilateral triangles is rigid. Yeah, because every triangle that sits on that you put onto an existing triangle, the angles are somehow quantized. Yeah, so you can only go tile it this way. Okay, so in that sense, topological crystallization implies geometric crystallization.
It's a unique configuration.
Sorry?
There's a unique configuration property. The triangular lattice.
Yes, exactly. And so the only freedom that is left then is 1 overall rigid rotation. So maybe, yeah, do we have a pen here? Yeah, maybe I draw it here. So the only degree of freedom, I mean, when you start the first triangle like this, no matter how you fit the other triangles, at the end of the day, you're only going to get these orientations here. And so the only thing you have is sort of an overall translation vector, and you have a sort of overall rotation. Oh, it's fine. I mean, so well, I mean, I think you can. I'm not going to draw it again for you. I'm sorry. So okay. So the only way you can patch triangles, equilateral triangles together in the plane is so the orientations stay rigid, but you have 1 overall angle of the configuration and 1 overall translation vector, and that's it. Okay, so that's the only freedom you have. And okay, so here we go. So now, so what I was saying is there's now the interplay between the perimeter and defect measure. So I have these 2 guys to play with, and so there's two operations. So the first thing is what happens if I have a configuration with simply closed boundary and I add a closed shell. By adding a closed shell, I mean what I picture here. So so I add one layer of atoms around the thing. Okay, and so there is a nice way. So you add every point in the lattice which is connected to the previous configuration by one edge. Okay, so these are these white particles here. And then I have an estimate on the perimeter. So it just goes up by at most 6. Okay, the perimeter goes up by at most 6. So that's an interesting fact. And you think, well, you know, how do I prove this? It's very simple. So so if you so for each so the points previously in the boundary of the configuration, they now become interior points. So after I've added the layer, its curvature goes down to 0. That means they have now 6 neighbors. And before, how many neighbors they had is told to me by this curvature, because the curvature was sort of 3 minus the number of edges in the unit sphere. So for example, let's take this particle on the top here. So its unit sphere has just one edge. Okay, so it had curvature 2. But if I add 3 particles, 1, 2, 3, then it's kind of at the end of the day, yeah. So that's what I add here, and so I add k of x plus 1 particles at most for each, and so then I can just do the sums here, and then I use the Gauss-Bonnet again. So the particles I add, so it's this sum over curvature plus 1 over the boundary particles, and then I can do the curvature sum with Gauss-Bonnet, so it gives me 6 times the Euler characteristic, plus I get the number of particles in the boundary here. So I think it's a very simple and nice argument. And so the number of boundary particles in the case of simply closed curves at the boundary is just the perimeter. Okay, and so the 6 that I add is the 6 from Gauss-Bonnet, together with the fact that the Euler characteristic is 1. So you know, I think that's one of the great things about this geometric thing. So that 6 comes from Gauss-Bonnet, yeah, and you add curvatures. So these arguments work very nicely with the curvatures. Okay, yeah. So that's this this lemma. So now I want to do so what one really wants to do is doing the opposite. So I want to see what happens when I remove the boundary from a possibly non-crystallized configuration. So then I hope very much that the perimeter will only drop by so that I can control how much the perimeter drops. And so it's sort of, I'm interested in the opposite lemma from here. So excuse me, yeah, the opposite thing. So now if I have this configuration and I subtract the boundary, what can I say then about the perimeter? Okay, and so that's the sort of central thing that makes this crystallization theorems for finite sets so hard. So these two examples are very, 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 very carefully chosen. So they're essentially unique. So for this size. So here's an example when you have a defect in the middle and you remove the boundary particles, what happens to the perimeter? So here let's count the edges. So you have 1, 2, and it's a pentagon. So 2 times 5 is 10. Okay. So the side has length 2 and I have 5 sides. So it has perimeter 10. Now, when I remove these light blue particles, I get the interior pentagon. So that's again a pentagon, but its side length is 1. Yeah, so it has 5 times 1 edges on the side. So I go from 10 to 5. The perimeter drops only by 5. That is terrible. The perimeter drops by only 5. And so here's a worse example. So you might say, well, for the Heitman-Radin model, because I have some elasticity here, so there's some stretched bonds here. So this cannot be a bond graph for the Heitman-Radin. So just in case you think that, I've drawn this other thing here. So they're basically in our paper. So I didn't draw them for you. I drew them for everybody. Okay. So this is the thing with equal bond lengths. So I put a terrible defect inside. I just put the wrong lattice inside. I put a square lattice inside, okay? And now I just add nice triangles on the outside. So they're all equilateral. So here all bond lengths are 1 in this situation. So that's a feasible competitor for Heitman-Radin. But it's like, you know, sometimes in machine learning, some algorithms are very stupid at detecting obvious things. So you have a question?
I think here the other one of the terms that you put the extra diagonal, that one is positive for the squares, right?
Yeah, but the other term is positive for the squares. But look at this term. We are looking at the perimeter here. So so the perimeter here, so let's do our usual count. So this has a 4-fold symmetry. So to count the edges, I only have to count one of the 4 pieces. So this piece is the same as this piece and so on. So let's count the edges on this piece. It's four edges, 1, 2, 3, 4. Yeah. And this whole thing times 4 because of the 5-fold symmetry, the 4-fold symmetry. So it's 16 edges. Now let's look at the blue thing in the middle. So it's basically the so if I take away all the boundary particles, so it's basically so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's basically has just 12 boundary edges. So again, so in this case, the perimeter drops only by 4. So and so near the boundary, both examples look similar to crystallized configurations. Yeah. So when you look at the boundary, it looks like a good configuration. And so so what happens? So basically, so that's the thing that took us a long time to figure out how to rule these things out. The key lemma then is the following. So here in the inside you have some kind of defect, and so the correct thing where the drop is at least 6 is you need to consider the perimeter and the defect measure together. So this number 6 for the drop can be restored when we account for defects. Okay, and when I added the closed shell. So you know, that's a bit related to Franz Merkel's talk yesterday, and also, you know, the discussions we had with Werner about the Burgers vector and so on. So you can tell by looking at the boundary that there are sort of defects inside. And so here, this version of this drop was really, so yeah, one day my co-worker Lucia De Luca came to the office and said, you know, look, I think I can really prove this now. And I thought, wow, great, you know, this is kind of the thing. I mean, we restore the number 6 by accounting for defects. So if you have any hard sphere, so this works only for hard sphere configurations, so particle distance bigger or equal 1, and all the edge lengths are 1. The Euclidean edge lengths are 1. So it's a Heitman-Radin type result. So then the X has simply closed boundary, and the interior has to be non-empty for this to work. So these are simple conditions, and then the drop is at least 6. So P of X plus mu of X bigger or equal P of X without the boundary plus mu of X without the boundary plus 6. And in fact, so that's the opposite inequality to the adding a closed shell, because when I added a closed shell, I had a crystallized configuration and I generated another crystallized one. So the mu was 0 when I added closed shells. So it's exactly the opposite. And so that's the winning thing. And so there's a fine point. So when the drop is exactly equal to 6, you can easily see that the defect measure stays the same. So when the drop is exactly 6, you don't lose defects. So I think that's a, you know, if you want, I mean, you can think of this as a Eulerian version of Burger's vector. So what's great about this is that I don't need a reference lattice. So it works for general configurations, or in let's say continuum mechanics terms, we stay in a Eulerian picture. So we don't look at things relative to a reference lattice here. So that's sort of one of the things that.
I may just say,
Yeah.
you realize
Yeah.
a good point about the Heitman gradient model, because it's, at the same time it's off lattice,
Yeah.
but then it keeps this distance to 1, so you can do your discrete, you know, you can do things that you cannot do with hard spheres at finite.
Yeah, exactly.
I think
So
that's
the
a good
stickiness is
point.
important. Yeah.
Exactly, that's a good point that allows you to make all your analysis. It gives you the whole week now. That's the point. Right?
Yeah, exactly. Yeah. So that's a sort of key thing. So I'm not going to prove the lemma here. So it comes obviously from some curvature bounds. So it's short. It's about 1 page in our paper. But I mean, once we have understood this drop, so then what I rather want to talk you through is the proof of the Heitman-Radin, and so this now really goes on 1 slide with these 2 lemmas. So I want to take time and talk about this slide. So it's not some, you know, messy estimate where you do 5 million things or whatever, but it's a sort of so it's different from the linear programming bound stuff where you go into some dual problem. I think tomorrow I talk a little bit about Wigner crystallization, where there is also a dual, but today I think we stick with this. And so it's basically a variational argument which is based on comparing to a good competitor. And so here's, and so this, looking at designing a competitor with the same number of particles, where it goes as follows. So I suppose that, okay, I do a sort of induction argument. I suppose the ground states are crystallized up to a certain number of particles. Yeah, and for sufficiently small number of particles, you prove it by hand or brute force, or, you know, check it by computer or whatever. I mean, I think you don't need a computer to check it. For 3 particles, they form a triangle. Okay, so the induction beginning here is not difficult. Okay, so that now you take an n particle minimizer, and what you need to show is the absence of defects. So you want to know that all particles inside are, so all faces inside are triangles. So this defect measure needs to be 0. And so now the first step is really the clever idea of Heitman and Radin. And I like it very much, and we kept it. So if you see a good thing, I mean, if it ain't broke, don't fix it, right? So we keep this wonderful idea from them. So you start from any minimizer, you know nothing about it, but what you can do is remove its boundary. So that's the good induction step. So remove the boundary. So that gives you a new configuration that I call X prime. So I know nothing about it except that it came from a ground state by removing the boundary. So then my competitor is the following. So I compare it to a ground state which has the same number of particles as this thing has after removing the boundary. Okay, so I remove the boundary, then I get the new guy which has fewer particles, and I compare that to, so I take the ground state for that. So that is already nicely crystallized, but it has the wrong number of particles. So then I just add particles at the boundary by adding as many as I need, maybe not a whole layer, but half a layer or whatever. I just add particles at the boundary, the right number of particles, and that gives me now a competitor.
But you don't know that X prime is a ground state.
No, I don't know that X prime is a ground state. So that's the 7 lines here that will show us that. So, and then it's a chain. I don't know that X prime is a ground state. It's just a, so it could be a non-ground state. So, and then I have this competitor here. And so here, so we assume here, okay, so that the number of particles that I removed are less or equal than one closed shell around the Y prime. If it's more than that, the argument becomes easier. Okay, so we assume that. So the number of boundary particles I removed are less or equal one closed shell around around this true ground state with fewer particles. Okay, so and then we do the following calculation. So the perimeter plus, so we consider perimeter and defect measure together. So that's if you want this Eulerian-Burgers vector philosophy, you need to know what the boundary is and you need to keep track of how many defects are inside. So, so this is clearly bigger or equal to perimeter plus defect measure of the guy with boundary removed plus 6. So the drop of the perimeter is at most 6. That was my lemma. So the drop of the perimeter is at most 6. So now this guy I can compare to the competitor Y prime, because Y prime is a minimizer, has the same number of particles as this guy. So I get less or equal perimeter plus defect of the Y prime plus 6, since this competitor with the same number of particles as the X prime is minimizer. Now then, this is equal to P of Y prime plus 6, since Y prime is crystallized. So that's sort of my induction hypothesis. I know that up to some number of particles, ground states are crystallized, and then I'm considering a particle number which is, say, one bigger or whatever. Okay, so then I know by the induction hypothesis that for guys with for fewer particles, crystallization wins. So I can drop the mu. And so then I can estimate that from below by the P of Y, because the perimeter growth is at most 6 when I add a closed shell. So then I've estimated this by perimeter of the Y. So I really used, so for the Y's, I really added the particles on the boundary. So then I used my lemma, how the perimeter grows when adding a closed shell. And here I used how the two of them together drop when I remove a closed shell. Okay, and so now this chain is cool because I know that X is a minimizer. So P plus mu of X is the energy of X. So, but up to the -3n, which was the trivial, term we to subtract, which is the same for all. And so if this is bigger or equal than that, and that was a minimizer, then all inequalities are equalities. So that's how I win. Now, so then this is equal to this, and then I also find because the first thing is an equality, I know that mu of X equals mu of X prime. That was sort of when the drop is exactly 6, then that's the same number of defects. So then I can figure out that the mu of X is equal to the mu of X prime. And then finally, but the equality in the second thing here, so between this and that, and the fact that Y prime is a minimizer, then X prime is also a minimizer. And by the induction hypothesis, it has no defects. So this way I kill the mu of X prime.
Which again shows the role of topological. I mean, this is a topological defect, and you cannot do anything between X and X prime to get this defect out. Or if you do it, then you see it below.
Yeah, then I would see a strict inequality somewhere here. So I think So that's really then the proof. So simultaneously doing this chain of 4 inequalities. So drop is at most 6 when you remove the boundary. Then you get a bigger or equal when you replace by a minimizer with fewer particles, of which you know it's crystallized. And then you add back a closed shell, and then the growth of the perimeter is at most 6. And then by this being minimizing, everything is equalities, and you control the defects and get zero. So I think that's a, I mean, to me, that's a kind of transparent argument that also ties in with the philosophy of defects versus perimeter and how they interplay. Okay, so here we go. So that was basically, yeah, are there any question or comments on this HR move? Yeah, I mean, we put the slides up so you can also, you know, look at it at home, or I mean, but it doesn't get shorter than this, I think. Yeah, please.
Yes. Comment on why this is not this case. Why is it much easier?
Sorry, why is it harder?
If you make this assumption, you say assume that size of the boundary is less than or equal to plus.
Okay, because you might, I mean, if the minimizer was ridiculous, you might have to move more than one closed shell. So so add more than one closed shell to the Y prime. And so then, but then, you know, you get even more addition. So I mean, it's just simpler here by sticking with one closed shell. If you have one closed shell plus half a second closed shell, etc. So you have to treat this case. So it's just so then essentially you have to apply this kind of inequality kind of twice, but the numbers go in the right way. So then the estimate gets even better. Okay, so yeah, any other question on this? So then I think, yeah, so that was my explanation of the Heitman-Radin. So the result then is we get this global rigidity of the minimizing configurations. So I think I want to go on Outlook. So I have lots of Outlook topics to discuss. So I mean, that was the theorem I wanted to prove, but sort of zillions of Outlooks. And I think I discussed slowly various Outlook things that are related to this kind of circle of ideas with these Lennard-Jones type interactions, which are attractive at short range, repulsive at short, attractive at long range. So the first thing is the uniqueness and non-uniqueness in the Heitman-Radin. So so yeah, that's the first interesting thing. So you think, you know, uniqueness is kind of boring, and I mean, yeah, so yeah, we thought with my coworker, we thought, yeah, no, maybe we should do the uniqueness, and so I mean, the first thing is when you start looking at examples, so the minimizers for Heitman-Radin are not that unique. So the first case where something new happens is n equals 5. Sorry, excuse me, n equals 6. So nothing happens until n equals 5. For n equals 6, you have 3 configurations that have the same energy and are minimizing, so it's non-unique. Then for 7, it gets unique again. For 8, it gets unique. For 9, you get 4 minimizers. I mean, you know, when you add an extra, you can do it in various places. Yeah, take this triangle and move it kind of like here, then you get this guy or whatever. Okay, 12 is nice. It's a non-symmetric but unique shape. I like the 12. So there's one shorter side. So 3 guys gang up against the 4th guy. So the 4th guy is shorter, and the 3 other guys, yeah, they rob him. So yeah, let's say, and so the sequence of uniqueness, I mean, I'm not going to tell you the combinatorics, but there is a combinatorics we worked out with the same methods when it's unique. So it's a little more tricky, and but we worked this out. So, but that's not the end of the story. So what's really interesting is what happens for large n. So go into the kind of statistical mechanics, zero temperature regime. So how large is the non-uniqueness? Well, so here's a picture of a typical configuration, which is a minimizer. Yeah, you add some particles on the boundary, and you start from this regular hexagonal shape. So that's always unique. See the sheet, and okay, if you got stuck, use the reference given on the sheet. But then these boundary atoms, I can move them around. It doesn't make any difference where I move. I mean, whether I move this last guy, I could move it on this side, yeah, because it has 3 neighbors, 1, 2, 3. If I move it over here, it still has 3 neighbors. So yeah, I can move the surface atoms around like a snake. Yeah, makes no difference. So here's a natural conjecture. So the atomistic non-uniqueness should be due only to the surface atoms, of which in 2 dimensions are order n to the 1/2. So in d dimensions, it's order of n to the d minus 1 over d. So if I have any 2 minimizing n particle configurations, and I take, let's say, the empirical measure here, so the mu is just take the sum of Dirac masses here, it's not renormalized, just the sum of Dirac masses, put them at x, and compare them in the total mass norm, then for Heitmann radian, the difference, if I'm allowed to rotate and translate, it should be of order n to the 1/2. So yeah, up to surface atoms, the thing should be unique because I have this global rigidity. Yeah, so the subsets of the lattice. So we thought for a while that this should be the case. Actually, when we was earlier on when we were working on when we didn't have this proof yet, but we were working with Bernd Schmidt, my graduate student. And so then maybe it's time to wake up in the morning because this is wrong. So the true amount of uniqueness is not of the order of the surface, is of the order of n to the 3/4 atoms. So it's now known as a sort of n to the 3/4 law, and was found by my coworker Bernd Schmidt. So so in fact, yeah, we sort of found the example that it can be this together, but he then found that this is the optimal law. So
Is that because the snake can be made into snake soup?
okay, let me maybe answer this on the board. So maybe I can be persuaded to take the black pen. So sorry, much. You know, I'm happy to draw with black pens, but I'm not happy to draw things twice. You know, when it's just triangles. Okay, so okay, so let's draw the argument why it's. So we can rearrange order n to the 3/4. So that's paper by Bernd Schmidt and Journal of Statistical Physics. So so let's start from yeah, okay, so I'm sure you want to see this. So maybe can we wipe the, do you have a cleaner for this or
Down there.
left, right? Oh, in here, oh my God. This far low down, I never always have my head in the clouds. I'm a mathematician, right? So here we go. So yeah, so this is how we do it. So let's start from a regular hexagon, and then we add sort of one particle here, yeah. So add one particle here. So that I can certainly do. Add one particle here. So that then would be a minimizer for these particles. So now then, what do I do next? I have one particle sitting here at this corner, which also has only, I mean, let's do this slowly and see what we have here. So this guy in the corner, it only has 3 neighbors. But if I put this guy here, it again has 3 neighbors. Yeah. So I can move this guy to kind of here. Okay. So it has the same number of neighbors. So now but I can keep doing this. And so let's look at the side lengths here. So this is the order of n to the 1/2. Okay. So like Alexander, I'm dropping all constants. So this length is n to the 1/2. Okay. So so then I can make a little hole here and, you know, remove the next particle, remove this guy, put it here, this guy, and so on. So then I get the following configuration. So that's so now I've added kind of a whole line of atoms here. So now what I have done is so I've added, so I've kind of added n to the 1/2 particles here. So let's do the count correctly. So so it's still n to the 1/2, but let's look at so this is n to the 1/2 particles I've changed. But so then what's the size of my hole? So the size of my hole is the following. So then this is n to the 1/4, and this is also n to the 1/4. Okay. So I've got a hole of size n to the 1/4 times n to the 1/4. So now, so what do I do next? So so I draw it again. So and then you see a kind of so what should I do next? So I do something that looks stupid, but it works very nicely. So so I now do the following. I just cut this piece here. I chop it off. And I put it here. I stick it on. Okay, so I chop off this piece and I stick it on here. And so now the piece I've moved, so this piece I've moved, it's now n to the 1/4 times, and this thing is n to the 1/2, because it's n to the 1/2 minus n to the 1/4, so that's still n to the 1/2. So I take this piece off, stick it on here, and so then this, so I've moved the, so this gives, so we have moved order n to the 3/4 particles. So that's the true amount of non-uniqueness. And then, so that's an interesting contrast with the continuum limit. So for these wolf shapes, I show you on the next slide, because there the minimizer is unique when you pass to a continuum limit. But here the non-uniqueness is surprisingly large.
Just an observation here.
Okay.
For me, it was at first I didn't realize. So that in all this business, you are just doing this in order to gain O of 1 of energy, right?
The energy stays the same. They all have the same energy. I'm not gaining. They're all ground states. So they're all minimizers. So in fact, so yeah, that answers also the question on the problem sheet. So I showed you on the problem sheet, there were 3 configurations. I asked you which of them are minimizers. The answer is all of them. They're all minimizers. Okay. So that's the answer to the sheet. So they're all, so the energy is equal of this and this. Because look here, I took a guy which has 3 neighbors and I put it here in a vacancy which also has 3 neighbors. So it has the same energy moving it here. And I keep going, and then this thing, I couldn't care less where I stick it on. Okay, so they all have the same energy. They're exact ground states. Okay, so so yeah, so that's this order n to the 3/4 law by Schmidt. And in fact, now the asymptotic constant is known in front, so it's not just, so he proved upper and lower bounds, but later people figured out. Sorry? How do I know that's optimal? Okay, so that I know from my from the crystallization theorem. So when you look at this, so we also showed that the boundary is a simply closed curve, and we have a way of telling the length of the curve as a function of n. So the number of so the perimeter of this thing is fixed. So and you compute the numerical value.
It could be, excuse me.
Yeah.
So alpha is n very large.
Yeah.
Random. What's the probability that it's unique?
Yeah, exactly. So that's so it's 0 because the sequence here has density 0. So I mean the gaps are getting bigger, so the probability is 0.
How do the gaps increase?
It's okay. How do the gaps increase with distance n? I think it's order square root n or something. So it's sort of order square root. Okay, so I think I think what is interesting here with this non-uniqueness would be to do the statistical mechanics at zero temperature. Okay, so statistical mechanics at zero temperature. So somehow these guys have more eccentricity, so there are more of them. So entropically, they should be favored. So when you look at random, you should be more likely to see these guys because they have more entropy.
Entropy becomes always like the TS, temperature.
Yeah, I understand. But sort of the statistical mechanics at zero temperature is you take the ground states and then let temperature go to zero, and you ask what is the limit as temperature goes to zero of the Gibbs measure. And so it will be a non-trivial measure, not supported on just one state, but it will be smeared out. It will be on one state if it's unique. So for some particle numbers, it will be unique. For some other particle numbers, will be smeared out. Okay, so here we go. So that was the non-uniqueness. Oh yeah, please.
Will it sometimes kind of, especially when you have multiple minimizers, exclude some and concentrate on things that,
Well,
or will the support be all of them?
the support will be all of them, but it will not be the uniform measure because they differ in entropy. They will not be equally likely because, I think they will not because of entropic reasons. So I mean, there's in any case the invariance under rotations, yeah. So of course, whatever you see, there is a uniform measure on this rigid translation and rotation. But when you rigidly rotate and translate this guy, you always get the same. But here you get something different. So there, in some sense, there are more of them. So okay, so here we go. So okay, so now the other thing I want to talk about the existence and uniqueness of the asymptotic shape. So we've moved order n to the 3/4 particles, and that's optimal. But you don't need this finer analysis to get the asymptotic shape. So that's a 10 years old theorem by myself and Johan Arjoing and Bernd Schmidt. So and I think it's still a very nice theorem, and it's kind of the only case where you really have a result like this. So if we take so that ties into Ed's talk earlier on this morning. So here we look at the empirical measure. So now it's rescaled in the same way as you rescaled it. So in the plane, so you rescale positions by 1/√n. So that the typical distance becomes 1/√n to get at the end a cluster of size 1 in the limit. It's just the same rescaling as you do. And then the 1/n to get a probability measure here. So that's the empirical measure. And so I think it's really an early paper using empirical measures on these deterministic problems. I don't know any earlier paper than that, actually. So and then as n goes to infinity and up to translation and rotation, the mu n converges to the characteristic function of a regular hexagon. So in this case, the limiting mu that Ed was talking about this morning for the confined Rees gases, it's really known. So it's the characteristic function of a hexagon. So basically this shape somehow wins in the limit because the order n to the 3/4, it gets killed by the 1/n here. Okay, so it's too few particles to matter in the limit. And so the proof sketch is you really do a sort of gamma convergence result. So we look at this energy and find out what the limit minimizes at the limit. So the limit, so we show that, so you get, so the density needs to become uniform on a set. So it's a uniform measure on a set. So this stuff that you were talking about this morning, that you have some singular piece on the boundary and something else, does not happen here. So it's really a uniform measure on some set, and the set satisfies a variational principle, namely it minimizes a certain surface energy. So you integrate a function of the normal over the boundary. So it's a surface integral. So among all shapes of the same volume, it minimizes a certain surface energy, which we figured out explicitly, and which favors these three crystalline phases. And we also computed how costly it is to have a wrong interface, which is not a lattice interface.
And this sequence is not a sequence of uniform, right? If you take any sequence,
Yeah.
going to any uniform and
Yeah.
I mean unique and not
Yeah.
unique.
Yeah, it's any. Yeah, it's any minimizing sequence. Okay, so and then okay, so and then the minimizer of this surface energy function. So we first find the limiting variational principle. So that involves some surface integral, even though the minimizing measure it sits on a set and is one there, but the set on which it sits is governed by a asymptotic variational principle. And that principle is kind of well known. So it's so there is a sort of, so for these kind of variation principle, it's known how to find the minimizer. It's something called the Wolf construction. And so the minimizer is the Wolf shape for the surface energy. And so the surface energy we get, it's basically looks like this. So I mean the formula won't help you, but if you have the normal with respect to the lattice orientation, so it's basically if you the angle of interface with respect to the lattice, if you draw this here, then you get a surface energy which looks like this. Okay, yeah, it should be like this. So it comes like this: 0, 2 pi over 6, ... So so this is the surface energy. So if you have a sort of off lattice interface, it sort of costs you surface energy. And so it looks exactly like you expect it to look. So it's Lipschitz. So but it has this sort of dips to the inside. And then for this, if you work out the Wolf shape by this construction, you get a regular hexagon. Okay, so that's the existence and uniqueness of shape. But I think it's the only case where for this Lennard-Jones type potentials, the limiting measure is known. So it's kind of pathetic. So yeah, I was thinking, should I mean, the natural parameter for us, which is like the S in Ed's work, would be the P in the Lennard-Jones. So at least for P close to infinity, the same bloody thing should happen. Everybody believes the same thing should happen. And
for this model, it's a bit more like compressed in the center and more rarified at the boundary, numerically.
No, it's I mean, the boundary layer should have finite range. I mean, it just should be a surface energy. So it has, because it's a summable thing. So when P is large, your potential is r to the minus p minus 2 to the r to the minus r to the minus 2p minus 2 r to the minus p. So when p is bigger than the space dimension, in this case 2, everything is summable. So all these boundary layers should have finite depth and decay nicely into the interior. So we think that this theorem should be true for large p, but pathetically it's No, I mean, I'm just saying P sufficiently large would already be nice. So P bigger than 1 million is not known. I mean, get a lower bound P. I mean, in practice, it should hold for the Lennard-Jones 612. So when you do simulations, it should certainly hold for P equals to 6. Let's say about, So it certainly should hold, but it's the only case where we know the measure. So maybe maybe over lunch we have to figure out another parameter we could add, which is easier than the P. Yeah, this question there.
Is there an idea of some gases where you can identify that the real model behavior at 0 to, and then what we solve is that at constant temperature, the temperature is not too big, you also get almost short convergence. Same thing. So is that also something that you can?
So positive temperature we have not studied, but it would be interesting. So, but I think for this Heitman radian, it hasn't been studied. So a lot of things are known for other models at positive temperature, like the hard non-sticky disks and so on. Then you need to speak to Werner here, who knows all about that, but not for the HR. So it would be interesting to do. Okay, so you know, maybe a related problem that has been done is for magnetizations when you have a background lattice and you look at magnetization, so spin systems. So there's a book by Krotetsky, Schlossman, and Dobrushin. So they wrote a very nice book about wolf shapes, but there you have a background lattice. And so what happens in the Heitman-Redin is a little more complicated because you don't have a background lattice. So when you allow a state that is slightly off the ground state, you can have some atoms that move somewhere else, you know. So it's not directly covered by the Dobrushin, Krotetsky, Schlossman on the lattice systems. Okay, so yeah, so this is the shape. So now soft potentials. So now it's going to become embarrassing. So what do we know about soft potentials? So yeah, I added this slide thing. Werner so told me I should add a slide on soft potentials. So here's my slide on top. So the best result that is known is a sort of existence of the bulk term in the expansion. So if you take a soft pair potential, which is sufficiently close to Heitman-Redin, so unfortunately in the paper, it doesn't say P sufficiently large because the story with the P was introduced by us like a few years later. So, I mean, there's some assumptions. So it has to have a very narrow well of depth -1 and you know, and then go quickly to 0 at long range. So the tile constitutive assumption, I mean, it's sort of constitutive assumptions on the potential which quantify the growth. So something like this. So it has here sort of fast decay. Here is 1. So that's the V, and this is the distance, and then you take here -1 and 0. So something like this, and so here it doesn't become rigid, but needs to fast growth to infinity. So it needs to go fast to infinity and fast to 0 here, and needs to have a and this thing needs to be narrow. Okay, so yeah, I remember sitting in a talk by Florian, sitting next to my co-worker Stefan Müller, and with whom I worked on other things like plate theory, and then so Florian explained his constitutive assumptions, and he called these potentials Lennard-Jones-like, and then Stefan asked me, yeah, but that doesn't seem to apply directly to Lennard-Jones. And I said, no. And then Stefan said, oh, now I get it. Lennard-Jones itself is not Lennard-Jones-like. So yeah, it's just the wording in the paper. I think if we checked, if somebody bothered to check, so the proof by tile, it would work for, I think it would work for large P. It's just not written up in that way. So, but I think the proof and the ideas, they should work for large P. Okay, so maybe somebody who, yeah, I mean, it would be a noble task to really check. So, okay, so, and the result is very, very nice. It's a super nice result. He says it's a soft potential sufficiently close to Heitman-Redin, then the ground state energy is a constant times particle number plus little o of n. Okay, so there exists a limiting energy per particle. And so what is the C? It's basically the same as the energy per particle in an infinite triangular lattice, but with relaxed lattice constant. So because the potential is kind of allowed to be long range here, it's not exactly 0. There is a little, so the bonds, I mean, there's a compressive contribution from the outer bonds that compresses the lattice a little bit. But so
not long range, not short range.
Sorry?
Not short range. It's compressive contribution.
It's not okay. It's okay. So there are different definitions of short range. So it is short range in the physicist sense that it's summable in 2 dimensions over a lattice. But it's
the contribution of next nearest and next nearest.
But it's not a nearest neighbor model. So even neighbors at distance 1 million neighbors contribute. So it just decays. So, you know, it can have an algebraic decay like r to the minus p at long range with large p. So in that sense, it's not short range. So it's not like a nearest neighbor or second neighbor.
It's short range, but not finite.
Yeah, it's short range, but not finite range. Maybe we should call it that. Yeah, that's good. It's short range, not finite. I like that wording. Yeah, so it's short range, but I mean fast decay as here. And then it produces some compression on the bonds, so to speak. And then the renormalized lattice, if you then just minimize out among triangular lattices of different lattice constant, you find the true lattice constant is like 0.9 or whatever, you know. Okay, and so this is the energy per particle. So that tells you, so that's similar to like the sphere packing things. So it tells you that the asymptotic energy per particle is correct by so you get the optimal asymptotic energy per particle from a lattice. Okay, so that's analogous to the setup of the sphere packing results. Usually, you say that you get the optimal density by a lattice. So it doesn't say that all minimizers are lattices, but it says you get the optimal energy per particle. So that's the best result known. It's a great result from 2006. And okay, so but here open question. So what's the order of the error? So we all believe it should be big O of n to the 1/2 here, because for the finite but short range, I mean, all this boundary layer stuff, so you get some, you know, oscillations near the boundary or whatever. It should be of the order of the surface area. So,
but I mean, I bet you one cookie that if you generate, I mean, you have this nice configuration with one declination, right? One five oriented and all the other 6. That's not a lattice, and probably it exceeds the Cn by a logarithm of n.
Yeah, but
and it kills the whole thing.
No, it doesn't kill the whole thing, because here I'm saying the ground state, because that thing it kills the proofs of the things, but that will not be a ground state, because in this model there is no incentive for this thing to form.
I understand.
So that's what I'm saying. So it kills the proofs of the thing, but not the thing. Then the second thing that's open. I mean, I think that's what I said in my. Okay, that's what I said in my announcement. So we have, I mean, this. So we're interested in the global rigidity of the minimizer. So in the Heitman-Radin, we had that all minimizers are globally close to some fixed lattice subset. So there is a global orientation, and so that is not known. Is there any kind of global rigidity of the minimizer? So by that I mean a statement in the sense that the distance to the nearest set of n particles sitting on the tile lattice, or the triangular lattice with the correct lattice constant, that this should also be little o of n. Yeah, so that's what one should think. Maybe there's a global rigidity, maybe not. So then the next thing that is also even not known, there's not even some kind of local rigidity of the minimizer. It's not really yeah, really, yeah. So you want to say something about
then,
that's.
And then I mean, there are two kinds of rigidity. Like there's compression from. I think you were discussing compression.
Well, also to shear everything.
And the other one is shear.
No, I mean rigidity with respect to everything. So I'm saying really globally close to a lattice state. So up to little of n. So, but here on this local rigidity, there is a very nice paper on Archive from 2020 by Friedrich, Kreutz, and Schmidt. So they studied the same question for the Heitman-Radin model. So they went back into, but there for the ground states thing was settled. So they were instead looking at the case when the energy is minimal up to a surface order. But for Heitman-Radin, so if the energy is optimal up to a surface order, and then they found a very nice structure that it's basically locally rigid. So you get an analogon of this measure here, like some. But it has internal grain boundaries. But you have an orientation which is locally constant instead of constant, and so up to a set of the order of Hausdorff dimension 1. Okay. And so you basically, at the order of the surface, if you have anything that's minimizing height and radian up to a surface term, then in the limit, it's like locally a polycrystal with locally constant orientations. So that's a very nice preprint. So if you're interested, you know, have a look or ask me about it. So this local rigidity. So it's a little bit easier to prove, but still it's not a simple paper. So, but maybe this local rigidity should be true for large P. Yeah, that was the soft potential stuff. I have lots of other outlooks. I mean, I could go, I don't know, till when should I go on?
I think that we are past so you can go on up to 12:50, and then we have a break.
12:50 or something.
Yeah, 12:50.
Okay, yes, so very good. Yeah, so yeah, sounds good. I will finish a little bit earlier, but I can then do some other updates. So I was also interested in some sort of topological data analysis of this MD simulations that I did. So I want to show you some. So what I mean by this. So here I simulate somehow this this thing, but I now draw the edges. Okay, so during the simulation. So that's again Langevin, but with the proper Lennard-Jones 612. So now P is back to 6. So here's what you get. So yeah, so finally it's kind of rigidified. So I think it's also good to move it a little bit backwards here with the slider. So to show you some defects. Yeah, so yeah, you know, here's a square, here's a square, here's a square, here's a square. So there's lots of defects opening up, and also the boundary looks funny. Here's the Pentagon. Yeah, so lots of things happen during the simulation, and this guy takes a long time to go in. And so what one can do along such a simulation, so this is highly non-equilibrium. So I started my configuration really far out of equilibrium. So I didn't distribute the momenta according to the Gibbs measure. Then I would wait forever for something to happen. I distribute the momenta according to the uniform measure in the simulation, yeah, to get really non-equilibrium to see how that. But then what you can do is you plot the evolution of my 3 contributions. So here's Euler characteristic, here's defect measure, and here's perimeter. So yeah, so they look like this. So let's start with it. So this is time, and here's perimeter. So the perimeter is kind of 0 because initially it's kind of a gas. So you have no edges, and then it goes up. You form this edgy stuff with hair sticking out and so on, and a funny irregular shape. So you get a pretty high perimeter, so 55 here, and then eventually it settles down up to small fluctuations to some decent value. Now the Euler characteristic, it goes down to actually 1. So 1 is what's predicted for minimizers. They're connected. So we saw that at the end, okay, for a long time it was 2. So that was this dangling thing that hadn't connected, and then it went down to 1. And the defect measure, it started at 0, because when you have a gas, there is no phases, so no defects. And then it went pretty high. You got sort of messy phases. So it says like you had more or less 18 squares in this, or maybe, you know, 17 squares plus 1 pentagon or something like this. And then it goes back down again. So you can sort of track a little bit the state of these things. And so I think what would be nice is connect this kind. So the Lennard-Jones fluid has been studied a lot in the physics literature. Also in 2 dimensions, it's interesting. It's also interesting in 3 dimensions. And I think what would be really nice is to connect sort of the scaling regimes a little bit better to the sort of phases that are kind of happening in these systems. So I think, so for example, here would be my, so in terms of now, since we have these nice invariants like the defect measure and the Euler characteristic, so if the Euler characteristic is order n and there are no defects, so Euler characteristic order n tells you you have n connected components, so that should be called a gas. If you have, okay, now it's a bit debatable, what kind of liquid, or whether, you know, other phases, I mean, there's sort of finer distinctions in the physics literature. But in a liquid, at least, I think, so the Euler characteristic should be of order 1, because typically you have a much smaller number of droplets than, I mean, yeah, and then, but then you should have many defects. So like order n, I mean, not n, but order n, because typically in a liquid, the configurations are not crystallized. So they're moving around a lot. And so maybe with plasticity, you have to be really careful what you mean by plasticity in terms of classical plasticity theory. So then certainly the defects need to be little O of n in the classical, so this is at least the classical theories of plasticity. Let's say little O of n, but this is with a lot of, you know, there's no atomistic definition, I guess, of plastic solid. And so for elastic, you should have more or less no defects and a single connected set. So that's just a vague thing. Yes, so Werner is sort of really unhappy. So yeah.
That's another subject. But what I mean is that this system at finite temperature has a finite number of defects. The question is how these defects interact.
Okay, so
the defects, so you have 5 and 7 coordinated, and then when they connect to each other, and in fact it's 5 and a 7 and a 7 and 5. I have pictures here, and they get together, and they have, now the question is whether they form, you know, whether they form ensembles of finite size or whether they are delocalized.
Whether they get extended,
So you have the 3 phases in this system. And but at any finite temperature, you have a finite number of people.
So what?
Finite density of people.
Okay, so finite density, but not finite number. So here n is really the particle number for me. So this is consistent with finite density. This is consistent with asymptotically zero density. I don't know. So and also there's a question of equilibrium versus non-equilibrium. So in the simulations I showed, they were really out of equilibrium. And so what you get in the intermediate stages, I think it's less. So what is better understood in the physics literature is at equilibrium. So because then you essentially sample from the Gibbs measure. And I think then there is a clearer picture. But in the dynamics, it's really not so clear what regimes you go through. But I think it's interesting. I mean, this non-equilibrium. I mean, if you run this, I mean, so this is what happens if you release vapor into some cold environment. I mean, there's lots of.
I did check. So slide referring to 2 dimensions or 3 dimensions.
Oh, my scaling laws were referring to. I mean, they were very vague. So you know, it's maybe. I mean, it's really very vague. So it's. I should have put question marks. I mean, you know, add lots of question marks. So, but I think this should be more or less. I think that the top and the bottom should be good in any dimension. But then I haven't defined what I would use as a defect measure in like 3 dimensions or higher dimensions. So yeah. Okay, so yeah, I mean the distinction between let's say liquid, hexatic, etc. I do not know whether one can capture it with these invariants. So I do not know. So the answer is I don't know. So this is a very vague slide. I mean, I mean, this is not a fact. I should have put a qualifier on the slide. You know, it's just for discussion. You know, that I think so. The message is just that this decomposition of energies into Euler characteristic, defect measure, and perimeter is useful to get a qualitative picture of what kind of state of matter you have and how it connects to classifications in the physics literature would be a subject for research, like with the hexatic. I mean,
I had a topological data analysis comment.
Oh, please, yes.
Which is that usually when you know it, because probably the first time I heard it was from you, which is that usually people are doing these persistence diagrams. So yeah. So your graph is going to look much nicer probably if you are putting this error bars alpha beta
Oh,
And then you study how.
yeah. Then I get more information. Absolutely. I played with the, you can play with the alpha and beta with sort of whatever you call a bond and not a bond, and then you get more information. I completely agree.
And people can study the stability for faster time distance of this.
Yeah, but I don't think they've done these nice MB simulations that I'm doing. So no, it's no, again, sorry, it's not a gradient flow. It's Langevin dynamics. It's not a gradient flow. It's a mixture of transport and diffusion, and the diffusion is only on Laplacian. It's not a gradient flow, explicitly not. It's not the Ornstein-Uhlenbeck process. So if you take overdamped Langevin, so you turn the second order dynamics, so this x dot, so let's say, so I did x dot equals p dot equals minus grad x v minus gamma x dot, that's the damping, plus sigma w dot. So this is Langevin. So what you are thinking is, if I do x dot, so this is the sort of Ornstein-Uhlenbeck, so it's x dot equals minus grad v. So then you only have x. So then you get a gradient flow. So this is not a gradient flow. So it's not a gradient flow. So it's a different thing, because you have, there's transport and the diffusion is only on the p. So the noise is added on the p. So in Langevin, the time derivative of position is always the velocity. That relation is not perturbed by noise. It's the forces are random, but not the fact that momentum is position dot. So that's a fact of nature. So that is not to be perturbed. Okay, so it's a different equation. So it has less damping. Well, it's and the generator of the equation mathematically is hypoelliptic. So it's not elliptic. So it has some directions in which it's not smoothing and blah blah blah. Okay, so here we go. So yeah, so I have other outlook stuff. Yeah, I can talk for a little bit. So here's an outlook, self-assembly of viruses, so protein crystallization. I happen to have a grant on this with a biophysicist from University of Potsdam, so we started getting interested in this. So here's some comments on this. So in atomic crystallization, you have a simple tile and a simple building, and in so we'll wait till the next slide. It's nicer. I'm not sure. So if you want to take a picture, take the next slide. It's not. So in a protein crystallization, in the virus self-assembly, it's the other way around. You have an extremely complicated tile, but a simple building. Okay, so it's a different game, and I would say neither math, physics, nor biology of this assembly are really well understood. So here's the tobacco mosaic virus. So that's the code protein. So it happens to have 1,284 atoms. So it's 794 carbon, 260 oxygen, 226 nitrogen, 1 sulfur, and 3 phosphorus. So you get these. So this is a visualization. It's by me. So I use the school chemistry colors. So I guess red should be oxygen in school, and gray should be carbon at school, and so green should be phosphorus. So that's a piece of the backbone helix, how it's assembled. And so this is, how I spend my time when other people watch Netflix. I go on the protein data bank. So it's the PDB, so the protein data bank. You can download the coordinate files, yeah. So of the things, then I put them into MATLAB because I hate their visualizations, because you get some fancy sheet bullshit that is overloaded with interpretation. I want to see where the bloody atoms are. So I wrote my own MATLAB, 10 lines, and to read it out, and then you can play with it and you can like rotate it. So you see how funny this shape looks. So it's a kind of very, very messy looking tile. Okay. So that's that thing. So if you look at it naively, you think, oh my God, what a mess. And but in fact, when you assemble it, it perfectly fits into each other. And so the building is a perfect helix. So it's a helix assembled from 1,283 copies of this thing. So this thing just nicely tiles the helix.
So it's a funny banana type shape, and you put the bananas like this, 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 and so then you get a beautiful regular helix. And in fact, you can also so yeah, the true thing is about 5 times as long. Yeah, so here I would say so when instead of Netflix, you know, I spend my time looking at these proteins. Okay, so you discover a lot of beauty in them. I mean, like, for example, I show you one detail which is nice. So if I zoom here a little bit, so let me zoom here. So for example, this thing is a little carbon ring, so it's a kind of benzene thing. So it's like a defensive thing. He sticks out a little molecule to defend himself. So, and there's a lot of little details you can discover when you look at these big proteins and sort of play with them. And yeah, so that's more, I think, a modeling challenge at the moment, because when you do protein assembly, what you should not do is do an all atom simulation. Nobody can do that. The system is too big and the interaction far too complicated, and there's no model. But one should find good coarse-grained models that assemble these kind of shapes. And yeah, yeah.
So those are tiles.
Yeah.
And how many number of them?
Oh, okay.
45 of them form the rest.
So I mean, so this thing sticking out is this piece of the tile. So yeah, so this is one tile, the second tile, the third. I have other pictures of them. Yeah, maybe I should have colored it gold and just plotted the shape. Yeah. So it's really just that. So what's clever about this virus is that its code is built from a single tile. It is only one protein. So you can ask, what's the biological advantage of that? Okay, so what's the biological advantage? Why does it want to have just one tail, one protein, and not many proteins? The answer was found by already goes back to a paper by Watson and Crick. So as of DNA fame, so they asked themselves this question. So the answer is pretty obvious. So when you think about it biologically, it needs less DNA to store to encode one protein, and so then it only needs a short stretch of DNA to store one protein. But then it builds, when it enters the host, so the tobacco plant, then it can produce many copies. And so the DNA strand of this virus is just as long as the helix. So it sits in the middle. I've not shown it. So it's sort of protected in the middle. So there's the DNA. It's like a little rope in the middle. And so it needs a short. So the thing these viruses solve is the problem: how can I build myself with very little DNA? So so therefore, so that's some of the biological reason for this small.
So there is no cap on the upper.
On the TMV, no, there's no cap. So the DNA is just sits inside. So it sort of bonds to the coat, and so it bonds to the coat, and then it's dangling inside to be sort of protected. So the coat serves to protect the DNA. Yeah, so that's the modern way of thinking, that the gene is everything, and we are nothing, our genes are everything, whatever, this Dawkins type stuff, whatever.
Something interesting. Can I ask for you?
Yeah.
So it was how do you get from the right to the left?
Yeah, exactly. So that's the assembly. So that's
how do you guess it?
Okay, so yeah, okay, so what we are exploring with my coworker, so we haven't, so we have 2 PhD students, one in Munich, one in Potsdam, working on this, on some simulations, is to really work with highly coarse-grained models. So in this case, you don't have a pair interaction between the proteins or something like this. It's a different kind of model. It's a coarse-grained model that has to do with the solvent accessible surface of the protein. So that goes a bit into physical chemistry models. And sort of surface models, and then so we have some nice simulations now that assemble 2D model proteins, but that won't get us into Science or Nature to assemble 2-dimensional model proteins. Okay, so we use there's more work to be done. Okay, so yeah, how do you get from here to here? So I think at the moment it's major a modeling challenge, because you need a model that is simple enough that that accounts for the shape, is simple enough, and is capable of doing the assembly. And so yeah, so it's at the moment like still at the modeling stage, because we are fooling around with different models. So yeah, that's this rotated thing I've done. So by the way, these pictures, so if you can read German, I mean, I wrote an article by special request by the editors after somebody heard a talk by me on this stuff. So it's the Journal of the German Math Society. So it's unfortunately in German, but the pictures are in color. So you know, I really, I don't know, you know, get your math society to translate it. I think it would be, I got a lot of emails because of this article actually. So yeah, Google it or whatever. So here we go. So yeah, Google Translate is on carefully written. So yeah, I have another slide is on Wigner crystallization. It's one slide. So so yeah, I maybe talk about, yeah, we can see what I do tomorrow. So at low density, if you have electrons confined by sufficiently uniform background, that due to strong quantum correlations, I believe to localize on a crystal lattice. So it was predicted by Wigner, and the first experiments on this are just a few years old. So in Science 2019. And so how to model this? So that's a sort of optimal transport problem with Coulomb cost. So it's a low density limit of quantum mechanics. And so the rigorous proof that this is really a low density limit of quantum mechanics is by Codina, myself, and another co-worker from 2018. And so there you basically minimize Coulomb repulsion, but over endpoint probability measures, but subject to a given 1-point marginal, which is uniform. So that's kind of the model. So you have an endpoint probability measure, not just the density. The density is really boring. It's uniform, but the endpoint probability measure is interesting because that contains the correlations. So yeah, that's another phenomenon. So if you, yeah, I have better I mean, this also, we have a survey article I didn't put on the slide. Maybe I talk about it tomorrow a little bit, but that's another nice sort of crystallization problem, which is Coulombic. But instead of the confinement by an external potential, you assume uniform background. So that makes it a little bit simpler to see what's going on, because you don't have to mess with the external potential. So you know, and here is a natural problem because of electron gases. So there's interesting stuff there. Yeah, I think I should stop at some point. Let me stop here and stop a little bit early so we have more time for lunch and discuss.
Okay, thank you. So are there any questions? Okay, so thank you very much.